So this is the video going over the solutions to the Chapter 2 multiple choice review. Some of these questions I've already written some stuff on just to make the video not so long, and then some I've left blank so far, and I'm going to write it all out, see if we can kind of practice the whole process together. Okay, so in this first one, we're given a lot of information. I kind of color-coded according to what was chemistry versus calculus. But basically, they're giving us all the things we need for z-scores. We have specific values. On a calculus and then also a chemistry final. We have means and standard deviations to go with them. They're basically telling us these distributions, and they said that they were normal. So this is just simply comparing the z-scores. So I did my z-score, value minus mean over standard deviation. And keep in mind, these are multiple choice, so you don't need to write out every little detail here. On free response, you would. So normally we'd write out the formula. Here I'm just kind of plugging it in. And I found out that both chemistry and calculus had the same z-score. So I don't need to go any farther than that to know who did better. They both did the same compared to other students in that subject. They both did a half a standard deviation better than average. So they did equally well. Number 2 is more about the concept of what standardized means. And remember, standardized is just a z-score. A z-score is just a standardized score. So because the scores that you're comparing before and after they changed it from seconds to minutes. So as in, if you're changing from seconds to minutes, you're dividing everything by 60. So before and after that dividing by 60, we're still talking about z-scores. And z-scores, standardized scores, are standardized. They are shifted and adjusted in order to make it so the center of their distribution is at 0 and the standard deviation is 1. So they can be compared to each other. Changing that dividing by 60 thing, that changing the units, does not affect the standardized score. It affects the original score, but not the standardized score, because the standardized kind of takes the units off of it, and it just makes it relative to the other points in their particular group. So z-score wouldn't change. It's still 1.72. On number 3, again, a conceptual question. So they said the distribution is not symmetric, so we know it is not normally distributed. So are we kind of allowed to still use z-scores is the question. Now, you can use z-scores on something that is not normal. A z-score is purely saying how many standard deviations are you above or below the mean. So it doesn't matter what the distribution of the data is. We can still be a certain amount above or below the mean. But in order to use table A, that's the big thing here. In order to use table A is assuming normality. If you look on the printout you have, there's a picture of a normal distribution up above it. Those percentiles are specific to a normal distribution. So you can go find z-scores, doesn't matter what the distribution is, but to use table A, you have to have a normal distribution. And we know we do not have a normal distribution here, so therefore we can't estimate it. We can't take that third quartile, which would give us 75th percentile, but then we would be stuck there because we can't use table A to turn that into a z-score. So can't do it. Okay, number 4, again, conceptual about what a z-score is. So the key here in B is they're saying it's 1.5 standard deviations above the average blood pressure. We don't know anything about specific data points because we don't have any of the other data. We don't know what kind of distribution it is or what the mean or standard deviation is, so we can't make a comment like this. C is missing the word standard deviation. It's not literally 1.5. It's 1.5 standard deviations. This is just not what z-score means. It's just, I don't even know what that is. And then E, that's related to percentiles. Technically, you'd have to go 1 minus that, or 100% minus 1.5 to get a percentile. But that isn't a z-score. That's a percentile. Okay, so the answer is B. Number 5, there's a lot of information in here. So again, I kind of color-coded it into the small puzzle and big puzzle. They did tell us things were normally distributed here. We have means and standard deviations and actual data points. So I went ahead and did the z-score for Shaylee's on the small and the large puzzle. And I just did the whole process where I looked for z-score, I used the z-score formula, And then I use table A to turn it into a percentile. Okay, now there is a tricky part here. And just be on the lookout for these things. Things here, greater than. They trick you a lot on these. So they want to know what percent is greater than Shaylee's, not less than. And table A gives you less than. It gives you everything to the left. So you have to be on the watch out for things like this: greater than, increase of, top, other words that talk that show you that it's to the right, not to the left. So these guys are to the left. So we still have to do 1 minus those to get our actual answers. So I really want, for the small puzzle, I really want 1 minus 0.8413, which is roughly 16%. It rounds to 16%. And for the large puzzle, I have to go 1 minus as well. So 1 minus, what was it? Basically 0.16. So 84%. So small is 16%, large is 84%. And I can guarantee you the most common mistake here is those two are switched because they didn't see the greater than. That greater than really matters. Be on the lookout for that. Okay, number 6 was calculation and conceptual. So we have 2 data points we're interested in, and one is given to us in terms of percentile, and one is given to us in terms of the original data value. So I needed to be able to compare them. So the first thing I did was I tackled this less than 90 bit, and I turned it into a z-score to figure out where that is. And it ended up being, I just guesstimated on the picture, right there-ish. And then they also wanted us to compare to the 80th percentile, and that ends up being, right here-ish. Okay, so we are interested in the percent of data that's here in between. So they are above the 80th percentile, and therefore they can get the certificate of merit, but they've also worked less than 90 hours. So that we need to find that percentage in there. So you can just I turned 1.43 into a percentage. So it's going to end up being, do I have room down here? Yeah, I'll do it in a better color. Easier to see. 0.9236, which is right here. Maybe I'll even label it 92.36 percentile right here. So 0.9236 minus 0.8 for 80, and I get 0.1236. Oh, something went wrong. This is what I get for not finishing the problem before I made the video. Okay, what did I do? So 0.9236 minus 80. Okay, I am going to pause the video and we're going to figure it out. I'm going to figure it out. All right, I figured it out, and I figured out I should not have assigned this problem because it is using a probability thing that we have not gotten to. And that is my bad. It's this word given here is getting into conditional probability, and that is like chapter 5. So we are far from that. So don't worry about number 6. I just saw the z-scores and got excited when I assigned it, but I missed that word given, which meant there's probability that's more complicated. So I will tell you guys not to do number 6. Okay. Number 7. Okay, very conceptual here. I made a graph just to kind of help us visualize it, but for the record, they never told us that 2 was the standard deviation. I'm making it look like that in the picture just to kind of spread things out, but the concept applies no matter what. But it's not like I know 2 is standard deviation. It could be very different than this. But what we do know is that 26 is in the middle. Okay, so I kind of have to think about all of these are chunks of data that are 4 ounces wide, so to speak. Like if I were to make a histogram or a bar graph, the bar would be 4 ounces wide. All these intervals are 4 ounces wide. So you have to think about which intervals in here would have the most data. So you could compare, say, 20 to 24 is right here. So this area represents all that data there. Compare that to 24 to 28. here to here, pretend that's symmetrical. There's a lot more green area than yellow area, right? We can pretend that's accurate. Because it's at the higher part of the graph. So conceptually, we need to be at the highest part of the graph that we can in order to encompass more data, in order to encompass more area on our normal curve there. So since it's centered around 26, then that means the interval that is centered around 26 will give us the biggest area. It's the chunk right in the middle. So that would be C. Okay. Number 8 is straight up z-scores. There's two values, 4 and 5, that you had to do z-scores for. So you can kind of follow my work here. I did the z-score formula, turned it into a z-scores, used table A to turn those into percentiles. And then I have my graphs over here. Here is my, oh, I didn't label them properly. Here is my normal distribution with my original data, so 4.6 and 0.6. And this is my standardized normal curve with 0, 1. Either way you think about it, it's still that same chunk in the middle, right? But if you turn it into a percentile in table A, now I can just subtract them to find the chunk in the middle. Okay. So this one is a good, just straight z-score percentile kind of problem. So I chose not to do this yet because I'm going to kind of let you practice it like a free response question. What all kind of work would you have to show? It is a multiple choice question, and a problem like this in the multiple choice, you don't have to show work. You just figure it out. But it's a good opportunity to practice all the stuff you need with a free response. Okay, so the first thing you need is your first original normal curve. It is approximately normal with a mean of 1200, standard deviation of 200. And we want the proportion of hours where the store exceeds 1400. So exceed, that means greater than, that means to the right. So if I put 1400 on here, it's just that distance to the right. Okay, and then we're going to eventually turn this into a standardized situation. So there's our standardized normal curve. The picture looks the same, and I want to know, what is that z-score? What's that z-score that is equivalent to 1400? Okay, so if this was a free response, you got your two pictures there. You need to write out the formula in words. So value minus mean over standard deviation. So in this case, 1400 minus 1200 over 200, which ends up being 1. They like giving z-scores of 1 and -1 in this review packet. So 1, we're 1 standard deviation above the mean. So let's go look that up in table A. So here's my table A, and I happen to be, let me get that back. Here's all our negatives. Here's all our positives. So if I look at 1.00, oh, let me make it so I can write on it. Oh my goodness. You guys are suffering through the most inefficient video. Let me bring it up as a PDF. Let me get a color going. Okay, so 1.0, 1.00, so I go 1.0, 1.00. So here is my percentile, 0.8413. So 0.8413. And we wanted to know how many exceed 1400. So I have to go 1 minus 0.8413. And I get, let's see, get my calculator, 1 minus 0.8413 is 0.1587, which is closest to 16%. Okay, so that, if this were a free response question, doing all that would give you all the points. You have both your pictures, you have the original z-score formula, you have your work shown on how you got to percentile, and you have a correct answer. Okay, the distribution of length of salmon is probably normal. Yep, so this is kind of a z-score one again, but with a twist to it. Okay, so we have a normal distribution. We don't know the mean, so I'm just I'll make it a question mark for now. We do know the standard deviation is 3.5. And we know that, again, we don't know the mean. We're up here at 30 inches, and I knew that was up at the upper end because they said 10% are longer. So again, that longer word, longer would be a bigger length. So we have 10% up here. So this is what we know. This is our situation. So I'm going to take that 10% and turn it into a percentile. Because if 10% is above, 90% is below. So I'm going to go look up 0.9000 in table A, and I'm just going to find as close as I can to that on table A. So 0.900, if we get a different color, 0.900, sometimes it's hard to find, looks like right here, because below that is 0.89. So if I trace that over, it's 1.29. 1.29 is our z-score. So 1.29 is my z-score. I do have my data point. My value is 30. I don't have my mean, so I'm just going to call that x divided by standard deviation, which is 3.5. And now I just do some algebra. So 1.29 times 3.5, 4.515 equals 30 minus x. Different ways you can solve this. I think it's easier to just put x on the other side. Now subtract. So however you did this, in the end, you should be going 30 minus 4.515. So 30 minus 4.515 is 25.485. And that is 26. Rounds to 26. Okay. And remember, there's a little bit of rounding error that happens with table A, and it's okay. I'm not worried about it. You shouldn't be worried about it either. Okay, back to a conceptual one, number 11. Which of the following is the best estimate of the standard deviation shown above? So this involves knowing, okay, the mean is 50. We know that. Mean goes right in the center. And we also know that going out 3 standard deviations gives you 99.7% of your data. So going out 3 standard deviations gives you 99.7%. So, I mean, like way out here is like nearly all my data, right? That's where the edges are. If I had to guesstimate, looks like it's going up by tens. So I'm going to guess 20 and 80 if I keep that scale going. So this is probably 3 standard deviations because it's covering nearly all my data. So it looks like the standard deviation is about 10. Just by knowing that if I go out 3 standard deviations, I should be essentially at the end of my graph with a little tiny bit left over. So there we go, 10. And that looks like the end. All right, Gerlicher out.